Let's get started. Good afternoon, everyone. Hopefully you don't fall asleep in this after lunch slot. This talk is about something that I think we all know, but maybe we don't know we know it in quite this way. Who knows Boolean Algebra? Pretty much everyone. Who uses Boolean Algebra every day? Everyone. In fact, that's all we do, right? In a very literal sense, that is all we do. The alternative title for this talk is a long one, which is why I didn't put it down, but the unreasonable effectiveness of Boolean algebra. And I'm going to talk about a message handling library, and there'll be a short excursion into the roots of programming. Okay, some front matter. My name is Ben. I work at Intel with Michael Case and Luke Valenti. All of the code you're going to see is open source. You can find it at this link. Of course, it's been simplified to slides a little bit, but you can find it. Do please ask questions as we go. And that's the front matter. Oh, and I feel the need to say that I don't really use LLMs in the creation of any talks. So this is all sort of my own thinking, but obviously I stand on the shoulders of giants. The other thing I want to say up front is, and this is a lesson I've learned, I just wanted to call out some of the things I use in my presentations in case they're useful to others. Accessibility matters, and there are easy steps we can take as presenters to make our presentations just a little bit more accessible. You don't have to be an expert. But I have had cases in the past where people couldn't read code on slides or whatever, and so I've taken steps to address that. Okay. This talk is about the workings of a message handling library. I'm going to introduce it. We're going to see just some code. We're going to see a lot of code, how we specify fields and messages, and then how we handle those messages when they come off the wire with matches, which are basically predicates. And then we're going to talk some about Boolean algebra to compose those matches. And then we're going to understand a little bit more about Boolean implication and see how that is the key to this whole library. And you're going to know everything that I say up here. Like this talk is a series of baby steps, right? Every step is a little bit more. By the end, I think we get somewhere really cool. So who has code that deals with, Chip has code. Who has code that deals with handling messages in some way? Yeah, it's real common, right? It's very common. Okay. Thanks to Augustus de Morgan and George Boole. These are two of the giants whose shoulders I stand on. I'd also like to thank my high school physics teacher, Trevor Huxtable, who taught me Boolean algebra. So, this code is open source. My colleague Luke likes to write issues, the one-liner, and assign them to me. And so he just wrote this issue which said, factor arbitrary matter expressions into sums of products expressions. He had this idea for building indices on fields in messages to be able to do fast dispatch. We'll talk a little bit about this. The talk about how to build the indices and what Luke did is actually a separate talk from this one, but it meshes in. He gave a talk in Aspen earlier on this year where he talked some about this. I'm going to cover just enough of it to give you a context. Anyway, that's all I had. So let's talk about fields and messages just to introduce you to the library. A field in this library is, we give it a name, we give it a type, and I work in embedded, so the type is almost always like UN32T, or something integral anyway. And then we have one or more locators that define how that field is located in the message. So it's message layout. Conventionally, that locator has three parts, which 32-bit word index it is, and then the range of bits. Because I'm working in embedded, I'm typically dealing with bits, not bytes. And that bit range is inclusive between least significant and most significant. Okay, so a field, let's think about something which may be familiar to a few folks. Here's the IPv4 header, straight from Wikipedia. It's got a bunch of fields, and we can see that some of the fields are bits, they're not bytes, right? So how would we declare those fields in this library? Well, we declare them something like this. So just the first 4 fields there. They all happen to be uint8ts. That's the type that the field presents in its API. And then the locators tell us which bits in the message they are. So you can see, the version field is the first 4 bits, 0 through 3. Then we've got the internet header length, DSCP, etc. Everyone good? These are all just using statements. They're declarations, right? There's no data here yet. Now, as you might expect, fields have 2 methods which characterize them, right? You can read from a message, or you can write into a message. And we call those extract and insert. And you give it a range, which is your message, an array of bytes or an array of 32-bit words or whatever. They do the thing you would expect them to do. Yes, and remember, a field is an empty data type. It's just defining where this thing lives. So we separate the name and type from the locator because fields with the same name and type might live in different places in different message types. Okay? Fair enough. And so there are a couple of different conventions here. One that's common is to use the D-word offset, but this is entirely equivalent to just specifying the raw bits, right? Luke likes to use the first one. Michael likes to use the second one. But these are entirely equivalent, right? Because, well, you can see 32 plus 18 is 50. You can see how these are equivalent. There's another thing we can do, which is, there's plenty of seats over on this side if you want to funnel in. There's another thing we can do, which is a use case, which is a field is split across more than one location, right? So it's still a uint8t when you read and write it, but the layout is split in the message. We actually do have this use case for a couple of things. And it works like this. Again, fairly easy to understand the declaration, I hope. OK, so now we have the idea of fields. We can put them together and make messages. And a message layout is just a named collection of fields. There it is, so the IPv4 header layout we saw earlier. That's a message with a name IPv4 and then a bunch of fields. That line 1 here is just an empty type, just a using declaration. When we want to put that together with some data, we can say, like line 3, here's an owning object, right? And that's the layout plus a right-sized array under the hood. And then there's get and set methods, which delegate to those extract and insert methods on the appropriate field. All good? Yes, nods. OK. Like I said, this is just introducing. So obviously, when we want to send a message, we normally own the data. So we have an owning type. And when we want to receive a message, we typically have a buffer. And we want to say, give me a view type over that buffer.
That's the West const.
That's a West const. No, it's not. It's different. It's a template. So already we can think that we can ask or assert properties of fields and messages. For example, we can make it a compile error to say the field's layout takes up 9 bits, but the API type is a uint8t. That would mean that you can represent more in the message than is representable in the type. That would just be a compile time error. And we can say things like that at compile time, right? OK, so that was fields and messages. They're really that simple. And that's just, I want to introduce the syntax. Let's talk now about how we match on those fields when they come off the wire. A matcher is just a predicate on a message, right? You give it a message, you call the function call operator, and it gives you back a bool, something convertible to a bool. But this is this is the concept, and you can imagine that the message is just a prototypical message here, because concepts, you can't constrain message in a concept like this. So this is just representative, but the concept is similar to this. So it's just a predicate function that returns a bool effectively, or a function object that returns a bool. Okay, so here is a really simple matcher. Like, let's say we want to say, I want to deal with a message a certain way if this field is a certain value. That's how we would write it here. This is an equal to matcher. We give it the field, and we give it at compile time the known value we want to handle. And it does the obvious thing. It gets the field out of the message we give it, and it says, does it equal that value? Right? Really simple. Matchers are empty function objects, as you can see. Okay. We can make that matcher a little bit more generic, right? Because this is testing equality, but we can pass in the operation, right? And the standard gives us stood less, stood equal to, etc. We can just take that out of the template, the relation, and call it a relational matcher now. And we get the convenience aliases where we just pass in the appropriate function object from the standard. Okay? It's a lot. Everyone's quiet. Okay, I hope that everyone's following. Okay, now here's the crux. I'm going to assert that matchers are the same as Booleans. They are isomorphic. A function that returns a Boolean we can treat exactly like a Boolean value. Normally we'd put together Booleans with ands and ors and nots. We can put these functions together with ands and ors and nots. What we're going to get is a expression template, which is itself a matcher, right? It's itself going to be a predicate, and it's going to work in terms of the underlying matchers that we gave it. Now again, I think you can guess how these work, right? Here's the and matcher. We give it two matchers, and there they are, just left-hand side and right-hand side. What's its function call operator going to do? Just going to evaluate the left-hand side and the right-hand side, and then and them together. Can you guess what OR looks like? Yeah, it looks exactly the same, except line 7, we OR them together. I mean, this is really obvious up to this point. And not is even simpler. I bet you can guess what that looks like. It takes one matcher, and it just returns the not of the matcher. Okay, so up to now, very, very easy stuff, right? So how does this build? Okay. Well, obviously, we're just going to overload the operators. I tend to use the alternative tokens just because I find them more readable. This is exactly like double ampersand, double bar, and bang, right? These are just alternative tokens. So these are operator overloads, and we return just the type of thing that we return, the obvious thing. Okay. Okay, so there's a bunch of different pieces. I want to show you a bit what the library looks like in use, in context, so you can sort of ground this a bit. More code, but let's take a look. Okay, so line 2 is a field definition called type. Line 4, we put that type field in a message layout. Right? We could have more fields, but this just has one. Then line 7, this is now we're getting to like what we actually want to do. We want to say, here's a callback. A callback is a combination of a matcher, how to recognize the message, and a function to call when we get that message. And so line 8 is an expression. It's a little DSL that gives us a matcher, right? In this case, it will give us that equal to matcher that we saw before. And then if that matches a message, we call the function on line 9, which does something. That's our dispatch, right? And then lines 12 through 17, that handler allows us to basically put multiple callbacks together and do the dispatch thing. And then line 16 and 17, you can see we've received a message in some kind of buffer, and then we're going to handle it. Cool? All right. This is what the DSL looks like to make it easy to write matchers at the call site, right? So you can say, I want this field to be this value. This other field can be one of two values. This third field can be some other constraint on it, right? So what we've done here is we've made it really easy for users of the library to write these things and write large expression templates potentially, right? Because this matcher is going to be that type under the hood. Okay, so I just want to be clear about notation here. I'm going to be using wedge for and v for or, and so I Googled what that symbol's called, and helpfully it's called not sign, according to Google, the bar with a tail thing. So what we've basically made is an expression template which represents some tree of predicates, right? We've got these predicates in a tree that are contained in this expression template type. We'd like to make sure that when we evaluate this at runtime, we don't do more work than we need to. We want to evaluate the minimum that we need to. Well, now, so this is where I came to the problem in thinking about how am I going to solve this problem that Luke put up. So I've made it easy for people to write these matches. And now I start thinking about, well, what kind of problems are they, what kind of things are they going to write, right? They might write, for example, if we look at less than 5 or greater equal 5, well, as humans, we know that that is always true, right? Some field is either going to be less than 5 or greater than or equal to 5. But these two types are entirely different. How are we going to tell the compiler that that's true, right? Likewise, if we say less than 5 and less than 7, well, that's just less than 5. If you're less than 5, you are automatically less than 7. So there'd be no need to evaluate that other side. Likewise, if you're not less than 5, you are greater than or equal to 5. The two terms in the last expression are the same term, really. So does anyone like the Feynman problem-solving algorithm? I like this algorithm. So what you do is write down the problem, think very hard, write down the solution. That's the Feynman problem-solving algorithm. You'd be surprised how many people don't do the first step. The first step is key. But anyway, I went away and I thought, and these were the kind of things I thought about, right? Like how are we going to tell the library to do this? Okay, so let's talk about that. Let's talk about how to simplify. So maybe many of you now are thinking like how you would do this. And knowing Boolean algebra, there are a bunch of rules that you can go to Wikipedia and you can see absorption, distribution, all that stuff. And there are sort of the normal rules that we all know. But these are all different types. What does the library need to know about these matches in order to simplify them? And importantly, how can it know that in a generic way? Well, I thought let's start with the obvious, really simple thing. Let's take a step back. The atoms of Boolean algebra are true and false. So let me just write those as matches. And they're easy to write. And I call them always and never, because true and false are obviously taken as words. Okay, so always is just always returning true, never always returns false. Straightforward so far. Now, if I think about this expression tree, now this library, back to Luke's original issue, this library meshes with another library that does indexing on fields. So imagine that you have a callback and you attach some matcher to it. Some of the fields that matcher references will be indexed, right? So that means that you'll be able to effectively remove them from evaluation in the matcher. And in that case, if C here, if we came out of an index, a code that does the indexing, and we know that C is always going to be true because we just indexed on that field. If we knew that, then we could simplify this whole thing. So not B or C is always going to be true. So that collapses. We don't need to evaluate B. A or true collapses to A, right? So the idea of like this library meshing with another is precisely that idea. You have a field or fields that you've indexed on. You want to remove them from this expression template. And then the whole tree may collapse, or parts of it may collapse. Okay, well, let's start going down this road. Let's write a simplify function. And it's going to be a function that we just overload for each type of matcher and see what we can do. If we can't do anything, then it's just the identity function, right? if we don't otherwise know how to simplify, we'll just have to give back the matcher as is. Now, and or look kind of similar. This is and on the slide. So naturally, we're going to try and simplify the left and right-hand side. And then we're going to try and ask questions about them based on sort of regular rules of Boolean algebra. So if after simplification, either one is never, then we know that the whole and term must be never, right? Because anything and false is false. Likewise, if either side is always, then the and must evaluate to whatever the other side evaluates to, right? And side note, if they're both always, actually, line 9 takes care of that as well, lines 8 and 9. Like if they're both always, then L is always, you're going to return always, right? But if we can't do any of that, then in the end, at line 13, we just say, well, we simplified the branches, and now we're just going to return the and. We can't do any better. So this is like a first cut at the simplification function for and. Yeah? Can the last line just return m? Well, we want to have simplified the left and right-hand side branches of m. So that's why lines 3 and 4 do that simplification, then we're returning the repackaged and, yeah. And the if const extras here are testing the types, right? Because we can do that. So it is known at compile time. Okay, so, I started writing this, and I'm like, there's a lot of these things, right? And for every operator, I have to deal with commutativity, right? Because and or are commutative. So I have to deal with a and true, and also true and a, and some of them I listed here. It's getting to be a lot, and it's a lot of code. And I don't like writing a lot of code when I think this should be more easily solvable. Yeah. So, okay, so I step back again. Yeah. And this doesn't even solve one of the problems I was thinking about, which is like, how does the library know that less than 5 and greater or equal 5, they have a relationship between them, right? We know as humans that these are inverses. How does the library know that, right? Because if the library saw, I would like to say, if you see less than 5 or greater or equal 5, that should simplify to always, right? Because I know that should work as a person. Okay. Well, in order to solve that problem, I thought, let's add another customization point. And let's this time customize not. Because if the library knew that these were inverses, then it knows that A or not A would be true, right? For example. So I thought, okay, let's have a go at customizing negation. Let's provide another function called negate. And instead of returning a not t from our not overload, we're going to return the negation of the matcher, right? Okay, so there's a couple of obvious things to start out here. The default thing, of course, for negate is going to be return a not t around it, right? Nobody answered. Maybe I'm starting to lose people. Everyone good with that? The default negation is still returning a not. What's the next obvious thing we can do? So not, yes. So if we're getting a not t, instead of double wrapping it, we'll just unwrap it when we negate it, okay? Like I said, there's baby steps, baby steps. Okay, yep. If we think about that relational matcher that we saw, we can invert the operation that it's working on, right? And we can say the negation of the relational matcher is another relational matcher whose operation is the inverse of the first one. And we can write, I think I wrote it's just a function with half a dozen if const extras in it, right? If you get stood less, return a stood greater, etc., etc. Just there's half a dozen of those operations in the library, right? All good? Cool. So now we've genericized this idea of complement or negation. So the library can understand things that, not just not t terms, but things we tell it are complements of each other, like less than 5 or greater or equal 5. And now it can attack this with its sort of normal Boolean simplifications because, well, we know this identity is true. All right, the next problem. Now this is a bit harder. Well, this requires a slightly different look at the problem, let's say. If I see as a human less than 5 and less than 7, then I know that should boil down to just less than 5, right? Because like I said before, if it feels less than 5, it is automatically less than 7. So I'd like to simplify this. Okay, this is where you do some work. I like to put quizzes in my talks, and here is a quiz. The questions, I hope, are very easy. There are no tricks. If they seem like trivial questions, it's because they are trivial questions. And the question is, can I obtain it? So I have from somewhere a thing of type A, doesn't matter from where, and I have a function from A's to B's. Again, I get the function from somewhere. So can I obtain a B?
Probably.
Yes. Okay, yes. Grizz said probably because, this is C++. But for my purposes, yes. Okay, yes. The answer is yes. Quite obviously, you just call the function with the A. Next question, same question, in fact. I have an A again. I have a function from A's to B's. Can I get a pair of A and B?
Yes.
Absolutely, I can. Again, you can make it so you can't because this is C++, but the obvious way to do it is just call f of A and get a B that way, and then you've got a pair of A and B. Final question. I have a variant of A and B, and a function from A's to B's. Can I still get a B? Yeah, right. Either the B's already in the variant, and I'm done, or there's an A in the variant, and I can call the function. All right, that was the quiz. That's all there is to it, and you would got 100%. So what was I talking about? You just did Boolean algebra, even if it didn't seem like it. You were reasoning about functions and types, but that was, in a very real sense, Boolean algebra. The question I want to ask you now is, what does that function arrow mean? What does it mean?
Return type.
It's a return type, but in a Boolean algebra sense, I see Lisa is smiling at the back. It means implication. A implies B. This is what we mean when we write a function prototype. Whenever you write a function prototype, what you're saying is A implies B is a true proposition. And when you provide the function body, you are proving that proposition, right? Let's look at those questions again and interpret them slightly differently. I'll give the Boolean interpretation alongside the C++ interpretation. When we say, I have an A, what we're saying is, A is a true proposition. When we say, I have a function from A to B, we're saying, A implies B is a true proposition. And when we're asking the question, can I obtain a B, we're asking, is B a true proposition? Right? When we say, can I obtain a pair of A and B, we're asking, is A and B a true proposition? And when we say, I have a variant of A and B, we are asking, we are warranting that A or B is a true proposition. And every time when we write that function expression, we're using Boolean implication, right? So, you knew the answer to those questions. The question is, how did you know? Because you know Boolean algebra, because you have this implicit knowledge of implication. And that's what it means. This is known as the Curry-Howard isomorphism, which is a term you may have heard of. Anytime we write types, we are warranting propositions. So when you write a function type, like I said, you are saying a function from A to B, you are saying A implies B is true. And when we write the function body, we're providing the proof of that proposition. And so we already know how implication works because we know how functions work. And so all we need to do is take that implicit understanding and make it explicit in Boolean algebra. So what's implication? Implication is a binary operation in Boolean algebra, just like and or. It's something that we don't use today very much in C++, but it has a truth table. So here's a truth table for and or, and implies laid out next to each other. So you're probably very familiar with the and or truth tables. You might be less familiar with the implies truth table. It is equivalent to not A or B. We'll use that fact later. But what I want to do is consider implication as its own operation, right? In particular, as humans, we tend to say things like A implies B, right? I think, and we sort of internalize that as, well, if A, then B. That sort of hides the fact that A implies B is a truth proposition itself. And so I tend to think it's simpler to think of that as a term, as a proposition like and or, as a function that produces a Boolean value.
Are you going to apply De Morgan to these?
Am I going to apply De Morgan? Eventually, yes. Not in this part, but in answer to Luke's question, yes. Now, I just want to spend a bit more time on implication because this is kind of outside of the wheelhouse of what we normally do and can be difficult to think about as humans. I want to draw your attention to a couple of propositions that are always true. So if we look back at this truth table, in fact, I think I have the truth table again. Okay, so there's a couple of propositions that are always true. Anything implies true is a true proposition. Right? We can get this from the truth table. I've just grayed out the lines that don't matter. But if we think about 0 implies 1 is 1, or false implies true is true, and true implies true is true. Lines 2 and 4 of the table. Okay, that's fairly easy to get your head around. The next one is harder to understand. False implies anything is a true statement. Again, we can look at the truth table. We can see false implies false is true. False implies true is also true. Grizz is smirking. So what does this mean exactly? This is hard to intuit, right? This is why I like to think of implication as a truth table rather than a sort of if-then statement. So I can ask you a question, what color is a unicorn? And I can assert truly that all unicorns have pink polka dots. Sorry, they're white, did you say? Well, they're white as well. That is true. That's a true statement. But I can say truly that all unicorns have pink polka dots. Because unicorns, of course, don't exist. The set of extant unicorns is the empty set. Any statement about them I can make is true. Here's a different explanation. Okay, so I can say, if it's raining, the ground is wet. That is an implication statement, right? It is raining implies the ground is wet. Now the question to ask yourself is, what would make that a false statement? The only thing that makes that false is if it's raining and somehow the ground is not wet, right? The ground might be wet for other reasons. If it's not raining, it's still true to say, if it's raining, the ground is wet. That implication proposition is still a true proposition. Yeah, and there are any number of reasons why the ground might be wet, okay? Here is a third way to think about implication. The set of times when it's raining is a subset of the set of times when the ground is wet. Yeah, think about that for a sec, and you can sort of convince yourself that's true as well, right? Saying the same thing, it's just a slightly different way. So there are a few ways to think about implication. Hopefully one of them clicks with you. Now, why have I spent 5 minutes talking about implication? Walter Brown has a paper introducing implication for C++. I read the paper. I thought it would be very useful, and so this was in my mind, luckily for this topic. And then I noticed something. So here's the truth tables again. and A and B, A or B, and A implies B. If I know that A implies B is a true proposition, I can take out that third line, because that's false. That's the A implies B false case, right? If I know that A implies B is true, then look at what happens to the other columns. A and B, that column is the same as A. A or B, that column is the same as B. So this, I realized, was the key to simplification. If I could warrant the truth of certain implication propositions to my library, it would know how to simplify and or expressions. This was the big realization I had. And it was serendipitous, you know. It was just because Walter's paper came out and I read through it and I was sort of wondering about this and I thought, what about implication? And then I wrote out this truth table and I saw this magical thing. Again, baby steps, but here they are. Here we are. Okay, so how would we use that to simplify? Back to this problem. Less than 5 and less than 7. So what this is really, when we say we know that this simplifies to less than 5 as humans, what we're actually saying in a Boolean sense is that we know that x less than 5 implies x less than 7 is a true proposition, right? And if we can state that in code, then the library has the keys it needs to simplify the expression. Because of the previous truth table where I struck out that line, we know that A implies B means that A and B will collapse to just A. All right, well, let's make an implies function. Let's kick the tires on this thing. What's the default going to be? Well, we know that A implies A, right? A thing implies itself is a true proposition. And in the general case, A implies B is not true, right? So we can write that with a one-liner here. So a thing implies itself. That's just saying return same as x and y. All right. Notice how these are all like one-liners, these functions. This is how you know you're going down the right path. When you're writing this nice composable library, and everything just turns out to be one-liner or a few lines. Okay, so here's the other fundamentals we saw. Here's the, what is this? This is anything implies true. That's the first overload here on line 1. We're saying anything implies true is a true statement, true proposition. On line 5, we're saying false implies anything. That is also a true statement, right? That was the unicorn thing. Now, if line 9 didn't exist, you'll notice that these overloads might be ambiguous in the case where we say, does never imply always. And that's just what that's just what line 9 is for. That's just an ambiguity breaker. So that's easy enough. These are the fundamentals that link true and false, if you like. Now we can just do a little bit of Boolean algebra manipulation here to find out how to write implies for and basically equivalently for or. They're joules of each other, so they work really similar. So, and here's literally what I scribbled down on some paper. X or Y implies A is the same thing as X and Y implies A is the same thing as not X or Y or A, right? It's the same according to the truth table. That's like A implies B is the same as not A or B. That's all that line 2 is. Then we can use De Morgan's law to push the not inside the and term, right? And flip it to or, line 3. Then we can kind of do distribution or idempotency, if you like, to get to line 4. And now what we see is, not X or A, that's the same thing as X implies A. And not Y or A is the same thing as Y implies, not Y or A is the same thing as Y implies A, right? So we've done just half a dozen, not even half a dozen lines of very simple Boolean algebra. And this tells us now how to write the implication overload for and very, very similarly for or. This is what they look like in code. This is saying exactly what the previous slide says, except in code. So does L and R imply M? Well, is that true? Well, that's true if either the left-hand side, either L implies M or R implies M, right? And likewise, does M imply L or R? Well, that's true if M implies L or M implies R, right? Again, one-liners. But these are sufficiently generic now to allow us to express a bunch of things. Like this is really straightforward one-liner code, but it's been genericized just enough to let the library deal with tons of different things. And now we can say things, so this is something extra we can do in the case of certain relational matches. Well, for the general case of relational matches, we can say that a term implies another term if the relation holds between what they're matching on. And the equality is there because, of course, A implies A is true, right? So this is saying that A less than 5 implies A less than 7 because, guess what? 5 is less than 7, right? That's what it's saying. And then we can go slightly further with some relational matches because we know there's a relationship, for instance, between less than or equal to and less than, and likewise greater than or equal to and greater than. So we can write a few more overloads to express those kinds of relationships. And this is the relationship between less than or equal to and less than. And again, it's a real simple relationship. You just have to say x is less than y. So this is what simplified looked like for and terms in the old style, when we were thinking about doing sort of the regular Boolean simplifications. And we were testing against nevers and always and whatever. When we change this to use implies, now we can write the whole function in terms of implies and negate. Right? We've customized these two things, negation and implication. And we can say, well, if the left-hand side implies the right-hand side, then we know that the and term collapses to just the left-hand side. That's what we saw in the truth table, right? When we struck out that third line, if the implication is true, then the and collapses to A. Likewise, the other way around is line 8 and 9. Line 10 is saying if either side implies the negation of the other side, then basically we're doing A and not A. So then we return never, right? And likewise, the last, line 13 is the catch-all, right? Where we've simplified both sides, we don't have any further way to simplify. And or looks almost the same, except dual. Basically, it's just very, very similar. You can see, in particular, line 10. Here we're saying for and if either side implies the negation of the other side. On line 10, we're saying if the dual version of that. So if the negation of either side implies the other side, then we return always. Okay, so we've customized negation, we've customized simplification, implication, right? Sorry, and we have simplified functions, and it turns out that's everything. It turns out that all of the simplifications, like identities, in the sense that true is the identity for and false is the identity for or, that just falls out because we wrote those overloads, right? Annihilation, idempotence, absorptions, it takes care of all of that. And all we did was look at the problem the right way, customize the right things, and write like one-liners. And the simplifier was like 4 different cases, but it's super simple. So now we have the expressive power of the matcher DSL. We have compile time simplification of these expressions, which gives us minimal work to do at runtime. There's my error on the slide. And we have, so this library is the matcher library. Actually, the message library I introduced at the start is sort of one library. And then the matcher library, the stuff that deals with the simplification and negation, that's an entirely separate library because all the message library needs to do is provide some like field matches and warrant some implications. And then there's another library that Luke talks about in his talk, which is the indexing on fields library. And they all fit together and they make the job easy and fast. Now, okay, I'm good on time. I'd like to make a couple of important points here. One is that, so the truth table for A implies B is the same as not A or B. Now, implication is, like I said, Walter Brown wrote a paper for implication in C++. And lots of folks are asking, well, why do we need it? Isn't it just not A or B? I think this application shows that they are different. They are the same truth table-wise, but I don't know how I could have written this code just by using not, and or. In the same way that like hardware does stuff with NAND gates, but we don't just have NAND in the standard, right? We use these things because they're useful. And in this application, it was useful to warrant implication as its own separate operation. I'm not going to say it's not possible to do with not and or, but it would have been much more difficult, and I certainly couldn't have seen how to do it, I don't think. The other point I realized a couple of weeks after writing this code was A implies B here is a true, if you like, a true higher order function. Like, we're composing matches directly. Like most higher order functions that we meet in any language, C++ included, things like algorithms or whatever, they end up evaluating the functions you give them. They compose them in some way, right? But they end up evaluating them. But here we've got them in the type signature. We actually compose them directly without evaluating them, and we eliminate them without evaluating them. So I just thought that was an interesting observation to make in this case. Okay. I have a couple of epilogues to give you, just to finish up here, because there are more interesting things to think about. Chris asked about De Morgan's laws, and there's also the distributive law, which we haven't really used. And these are used for the field indexing operations. Luke talks about it a lot in his talk from C++ Now 2024, which just came out on YouTube. So I'd recommend watching that. It's kind of a sister talk to this one. So remember this. So this one line of GitHub issue, which was Luke thinking about how to make indices. And the way he thought to make them was, if we have an expression, what we want to do is make it so that it's basically a sum of products or an or of ands, right? We want to make it into a form where the top levels are all A or B or C or D, and then A, B, C, and D could themselves be and terms or not terms, but there's no ors inside those ands, right? Because if we have it in that form, then we can walk the tree. When we see a field that we want to index on, we can sort of mark that in a table. We can make sets of callbacks. And the idea behind his indexing library is that callbacks are represented as like bit sets, for example, right? So you have a match, you index on a field. Let's say a field is 42. You look that up in an array, it gives you a bit set of matches to call that correspond to, of callbacks. A bit set that corresponds to callbacks to call when that field is 42, right? And then you've got another field, which is like 17, say. So you look that up in your index, and it gives you another bit set of callbacks to call. And then you AND together those bit sets, and you get the callbacks to call when you've got both 42 and 17, right? So the way the index works is fundamentally a sum of products, right? Because you've got the bit sets represent the fields, and you're ANDing them together, right? And you've built it by separating out the OR terms, if you like, over the different fields. I hope that was a clear explanation, or at least a reasonable explanation. You can watch Luke's talk for way more on that. So what does that mean? Well, you know, Wikipedia and the mathematical literature calls this disjunctive normal form. So this is what we mean when we say a sum of products or an or of ands. The term is disjunctive normal form. So like I say, it's at the top level. We've just got A or B or C or D. And A, B, C, and D are themselves terms, but there's no ors inside of ands. You know, the nots are all at the bottom level. Here's some examples. So the first line here, this is in disjunctive normal form, right? The top level's an or, underneath that is just ands. Likewise, the second line. Third line isn't because we've got a not outside of the or. And the fourth line isn't because we've got, what we've got an and at the top level and there's an or inside it. Okay? Everyone good with disjunctive normal form? So how do we transform this into, how do we transform an expression into disjunctive normal form? And this is where we use distributive law and De Morgan's laws. If you like, these were the two parts that we hadn't used yet. So recall that and distributes over or in this way. A and B or C is the same as, just like A times B plus C is A times B plus A times C. And or have the same relationship here. And De Morgan's laws is where we push the not in and flip the and to its, or the or to its dual. I imagine most people are familiar with these laws, right? Yeah, okay. So how are we going to write sum of products? Well, we're going to write it with a customization point, same way as we did the others. And the default thing is, of course, the identity, if we don't know what to do otherwise. Again, a one-liner. And now we need to implement the transformation, the sum of products transformation for and, or, and not. Sum of products for not, well, we're basically going to ask what's inside the not. Because if it's a single term, that's fine. But if it's an and, if it's an and or an or, we're basically going to do De Morgan's laws by pushing the not in to the internal terms, right? So we're going to negate the left-hand side, negate the right-hand side, then do sum of products on them to bubble the ors to the top, and then all them together. And that's the first case. Yes, question?
You had these if context first comments out very early in the presentation.
Yeah.
Can you explain what those look like?
Yeah, so this is, so I just commented out to avoid noise on slide and things that were distracting. But basically this is saying, is M a specialization of and T? Right, so you can imagine writing like in the simple case, writing a function overload, right? Which if it takes and T of L and R returns true type, and if it takes something else returns false type, you could do it that way. There are several ways you can do it, but basically that's what these if context expressions are doing, okay? So if it's an and, we push the not in, and we do De Morgan's, and we get an or. If it's an or, again, we push the not in. This time we've got ands, and we want to run sum of products on that again because there might still be an or inside it, right? Because sum of products always returns, basically always returns an or. It might be a degenerate or, which is just one term, but in general, it's going to return an or term, and we're anding together the or terms. So we need to do another sum of products on the outside to just kind of push that in. That was not, and is, so not does De Morgan's laws, right? The sum of products for and does distributive law. So if it's an or, if either side is an or, we're going to distribute over that or, either on the left or on the right. That's what we're doing in these two branches. And then finally, of course, if nothing else, we just have to return the and as is. So that's where De Morgan's law comes in. That's where distributive law comes in. Or is real simple, because or we've already got, it's already in an or form, right? So all we need to do is recursively apply the sum of products to its left and right branches. We know that what we get back from there is an or, and we can just or them together, and we're still in sum of products form. At this point, I could say, you might have wondered, I chose to stick with strictly binary templates here. I could have done variadic templates, right? But I stuck with binary and binary or because these functions were much easier to write just considering the two branches and not going variadic. So that's why I did that. But it would be possible, perhaps, to do variadic. I don't know. I just wanted to keep the code simple. So what is this bias? So disjunctive normal form, as I said before, is used to build the indices. We just basically walk the tree and we take the fields out, put them in the index, and we turn that matcher to an always, because we know that when we come out of the indexing operation, we've already dealt with that, like it's true in some sense in this matcher. So we can take those out of the matcher. Okay. Epilogue. Yeah, it comes from the Greek. I looked it up. I realized that, so a few weeks later after writing these matches and manipulations, I thought to myself, what does it mean for matches to be ordered, right? Normally we don't order functions, but we could order predicates. And what it means intuitively is that if one predicate is less than another, it means it's more constrained. It matches fewer things, right? That's what kind of an intuitive less than means on predicates. And what that means is that a larger predicate, no, a lesser predicate implies a greater predicate, right? So in a sense, the implication arrow is sort of the wrong way around if you want to think about it that way, but you just have to deal with that. These operators are runes, they're not composable pieces. And of course, if two matches imply each other, then that's equivalency, right? Let me do that in diagram form to make it maybe a bit easier. If A is greater than B, the set of things that A matches is bigger than the set of things that B matches. That means that if B is true, A is true. In other words, B implies A, right? Now, this diagram might be drawn as A and B entirely coincident. That would be implication as well, but the general case is easier to see. So that might be, doesn't have to be strict subset or strict superset. And this is kind of a new, for me, an intuition for that strange thing of false implies anything. Well, false is the empty set, right? Matches nothing. That is a subset of any set we care to name, right? Which is kind of why it implies anything in the set interpretation, I guess. It's like, I'm not trying to be mathematically rigorous here. This is just an intuition. It's a helpful explanation. Well, now we can write operator spaceship, right? So we can say, let's simplify both sides that we're comparing. Let's check if either one implies the other. If neither one implies the other, then they're unordered. This is a partial ordering, right? Because those sets could be completely disjoint. But if either one implies the other, then we have an ordering between them. We have operator spaceship. And this is the code. Again, it's not very much code. So I hope that, this talk, I like this library because it's just so many small composable functions. It starts from something we all know, but we never really think about day to day. And it's the same for me. But I just found that building up in baby steps led to this really cool place where the library does tons of stuff. And it's all down to just applying the very basics and just sort of thinking about them for me in a slightly new way. So thank you very much. I might have time for one question. Chip. Oh, yeah, go ahead.
Great talk. I'm interested. Have you checked if the compiler does the same or some subset of optimizations like you described?
Does the compiler do it? So in sort of regular code, the compiler, I don't know how the compiler works internally. It can see through some of these things, but remember we're marrying up 3 different libraries here. It can't see across boundaries. I don't want to rely on it seeing across those kind of boundaries. In some cases, it may. I don't know if it works like this under the hood the same way, but yes.
Thank you.
Go ahead. You've got 15 seconds.
All right. The less than 5 or greater equal 5 example struck me as like a little bit convenient because they're exact inverses. I felt like less than 5 or greater equal 4 would be kind of a gotcha. But then when I saw what you did with implies, I came away pretty much convinced that, yeah, it would probably handle that too. So do you know if it does? Does it?
It does. I have an extensive test suite where I test all those kind of things. And one of the slides was, in particular, there's a relationship between less than, or equal to. So all of those are encoded.
Yeah, that was the slide that
Yeah.
convinced. That's very cool. Thanks.
Thank you. Thanks, everyone. Have a great conference.